Ideal gas mixtures. A mixture, it's made up of something like carbon dioxide, maybe oxygen, maybe nitrogen, maybe argon, and it's going to do the same things that we have had pure substances do. Maybe it'll undergo a process in a closed system. Maybe it'll be compressed or expanded or heated. Or it could flow through a component. We have open system analysis. Maybe it flows through a compressor. Maybe it flows through a turbine. Maybe it flows through a heat exchanger. But we have to deal with mixtures, ideal gas mixtures. Then the last part of this chapter deals with psychrometric applications, basically the study of moist air. And moist air is very important because that's what we inhale and exhale. And that water vapor, H2O, also behaves as an ideal gas in our moist air mixtures. Once we have the concepts of moist air, how it's heated, how it's cooled, how it's humidified, and when you cool it, sometimes you hit the dew point and it's dehumidified. So when we talk about ideal gas mixtures, we review a molar description or a mass description of our mixture. So when you talk about the number of moles of a species I, that's just the number of kilomoles of component or species I in the mixture. Okay? And you have N will be the total number of kilomoles of the mixture. That's our notation. N sub I and N. Sometimes I'll say N mix, but it just makes for long subscripts. So the book just uses N without a subscript is the total number of moles that are in that mixture. Well, does it make sense that N is related to the sum of the NI's like this? It's equal to the sum of the amounts of each of the components in our mixture. We also define mole fraction. The symbols used in this textbook is Y sub I. It's defined as the amount of component I compared to the amount of all of the mixture. Okay? So if you take this equation, N is equal to the sum of NI's, you divide both sides by N, the N, 1 over N goes inside that summation, and what you find is 1 is equal to the sum of yi's. Hey, the sum of the mole fractions has to equal unity, 100%. I think that was pretty obvious. Let's go to a mass description. So we'll introduce the concept of MI, not to be confused with NI, right? M for mass. So it's the mass of species or component. I use those words interchangeably. You know, it's component I or species I. That's MI. Well, what's M? That's the total mass of the mixture. How are they related? Well, M is the sum of MI. Do I have to derive that? Not really. It's just if I sum up all the component masses, it's equal to the total mass. Well, we're introduced to the mass fraction. Subscript I is the mass fraction of the component I. Now, that's a little rare that you have two letters for a symbol, like T is for temperature, not TE for temperature, or PE. It's just P for pressure, right? But here you have MF for mass fraction, subscript I. Good. How is it defined? It's defined as the mass divided by the mixture mass, the component mass divided by the mixture mass. So it's the fraction of the mass that is species I. Well, you can do the same thing. Start from this equation, just write it down and say, okay, we have M is equal to the sum of MI's, divide both sides by M. That seems ridiculous on the left, but hey, on the right, it goes inside the integral or inside the summation, and you're left with 1 equal to the sum of MFI's. So the sum of the mass fractions must equal unity, 100%. What's the relationship between a molar description of our ideal gas mixtures and a mass description of our ideal gas mixtures, and how can we jump back and forth between them? Well, you jump back and forth. This is the key, cap m sub I. What's that? It's the molar mass. Remember, or molecular weight for each species. So what are the units on this one? Kilowatt per kilowatt. Kilogram per kilomole. So how do we use it? Well, if we have so many kilomoles of our species I, we multiply by the molar mass, and what does that give us? The mass of I. So Mi is equal to the molar mass times the amount. Rewrite this. If you wanted to get n sub I, it's equal to m sub I divided by cap m sub I. So you can move back and forth between a molar description to mass or mass to molar. Well, what was big M sub I? It's the mass of the species I divided by the amount of species I. That's how you would get it. If somebody said, I don't know the molar mass, but I could tell you there's 5 kilograms in this container of this species, and it's only 1 kilomole in there of that species. Well, it's 5 over 1. Its molar mass is 5. So if you have a mixture, you like to work with a mixture molar mass. That's cap M. So the mixture molar mass, or the apparent molar mass, okay? Large M without a subscript I. What's it defined as? Well, it's defined as the mass of the mixture divided by the number of moles in the mixture. Well, we can start with the equation that's simple. We say the mass is equal to the sum of the component masses. Then divide both sides by n. Divide that side by n. But you also realize that m sub I, right here, can be expressed as n sub I times the molar mass of I. And so what we find is that the apparent molar mass is equal to the sum of n sub I over n's yi's mi. Dalton's model for partial pressures. Let me just go ahead and read this. A mixture of several ideal gases. In this illustration, I tried to show blue and red, kind of in a mixture of molecules. Okay. So continuing to read, the mixture of several ideal gases will have a total pressure equal to the sum of the pressures exerted by each of the constituents as if they were alone at the same temperature and volume as the original mixture. So this original mixture has a volume, and we think conceptually of having it split into 2 components. Here I just have 2 components for illustration, and each of those containers have the same volume, the same volume, and each has the same temperature. And what we find is that the pressure of the original system containing both components is related to the pressure of the one component, let's call it 1, and the pressure of the second component. Well, they always behave as an ideal gas, and now let's derive that relationship between P1 and P, or P2 and P. So if they always behave as an ideal gas, it's N R bar T over V. What did I just use? I needed to put a bar on that, right? What did I just write? The ideal gas equation. Can you write it over here? Now we're going to have the number of moles of that species, R bar T over V. So the same T and the same V. So if we take this equation right here and we divide both sides by P, the total pressure, here we're going to divide by total number of moles, R bar T divided by V, then it simplifies that we have the pressure, we're going to call it the partial pressure, associated with the first component divided by the total gas pressure is equal to, a lot of things cancel, but it's the amount of component 1 divided by the total amount of the mixture, which is simply y sub 1. Or in general, we have that the partial pressure, instead of just thinking of 1 and 2 components, let's let I be the general 1, 2, 3, all the way to how many number of components you have. That partial pressure is equal to the mole fraction of that component times the total gas pressure. So this is the partial pressure. Have you seen that before? It's used a lot when you have ideal gas mixtures. The concept of a partial pressure comes from Dalton's law, or Dalton's model. All right. Let's go ahead and take a look at solving a problem. The molar analysis of a gas mixture is 40% nitrogen, 30% carbon dioxide, 30% methane. The gas mixture is at a temperature of 330 Kelvin and a pressure of 150 kilopascal. Determine the mixture molar mass. What are we asked to solve for? The mixture molar mass, cap M, with no subscript. Let's look at part B. What is determine the analysis in terms of mass fractions? So we're going to be looking for the mass fraction of nitrogen, the mass fraction of carbon dioxide. Oops, I wrote down Y. What does that mean? I'm looking for the molar fractions. No, I need the mass fractions, right? Mass fraction of nitrogen, mass fraction of carbon dioxide, and the mass fraction of methane. So those three things we need to calculate for part B. Part C, what's the partial pressure of each component? So we need the partial pressure of nitrogen, the partial pressure of CO2, the partial pressure of CH4. Notice that the partial pressure is given in kilopascal, the units. So partial pressure has units of pressure. And then the volume occupied by 1.8 kilomole of the mixture. So we want to calculate this volume when there just happens to be 1.8 kilomoles. Let's just call it the volume for answer to part D. Because in the part E it says what's the volume occupied when you have 29 kilograms of the mixture. That's the volume answer for part E. There's just two volumes. Just need to calculate two volumes. All right, how do we answer the question for the mixture molar mass? Well, we're given Y of N2, Y of CO2, and Y of CH4. We're given those mole fractions because it's a molar analysis. If you assume that the total number of moles is 1 of the mixture, this is a starting point, one way of doing it. Just assume the total number of moles is 1 for the mixture. Then we know that the number of moles of N2 is how many? 0.4 kilomoles. And the number of moles of CO2 is 0.3 kilomoles. And the number of moles of CH4 is 0.3 kilomoles. True? If you sum them up, you're going to get back to 1 kilomole. If I said, I know the molar mass of nitrogen, I have to look it up, but it's 28.01 kilograms per kilomole, then I can say that the mass of the nitrogen is the product of N times cap M. So we find out that that's 11.204 kilograms. So if I have a starting mixture of 1 kilomole, then I have in that 11.204 kilograms of nitrogen. Likewise, the molar mass of the carbon dioxide, 44.01 kilograms per kilomole. And the mass of the carbon dioxide is 13.203 kilograms. And the molar mass of the methane, CH4, is 16.04 kilograms per kilomole. So you get a mass of CH4 to be 4.812 kilograms. You can sum that up and you find that it's 29.219 kilograms. So we started with a mixture of 1 kilomole. and we find out the total mass of that mixture is 29.219 kilograms. So what's the molar mass of the mixture? M divided by N. We assumed this. We started with that. So its molar mass is 29.2 kilograms per kilomole. What is the mass fraction? Well, the mass fraction of the nitrogen, is that going to be the mass of the nitrogen divided by the total mass of the mixture? And the mass of the nitrogen, 11.204 kilograms and 29.219 kilograms, giving us a mass fraction to be right at 38.3%. And then you do the same thing, the mass fraction of the carbon dioxide. So it's going to be the mass of the carbon dioxide, 13.203 divided by 29.219. It comes right in at 45.2%. And the mass fraction of the methane comes in at 16.5%. You sum up those mass fractions to check, yes, it's 100%. It's kind of hard to box this answer, but I'm going to box it like this, and you know that's what I'm looking for the mass fractions. What about the partial pressure of each component in kilopascal? Is the partial pressure of the nitrogen equal to the mole fraction of the nitrogen times the total gas pressure? Partial pressure of the nitrogen is 40% of 150 kilopascal. So it's 60 kilopascal. And then the partial pressure of the carbon dioxide is 30% of the 150 kilopascal. So it's 45 kPa. And the partial pressure of the methane, CH4, is 45 kPa. Now, what's the volume occupied by 1.8 kilomoles of the mixture for the answer to part D? And we're going to use the ideal gas equation. The number of moles, because it's given to be 1.8 kilomoles, times R bar, times the temperature divided by the total pressure. 1.8 kilomoles, 8.314 kilopascal meter cubed per kilomole Kelvin. That's R bar, the universal gas constant. Then we have the temperature, 330 Kelvin, and you divide by the pressure. The pressure is 150 kilopascal, and so you see the kilopascals cancel, the kelvins cancel, kilomoles cancel. You're left with units of meter cubed. So the volume is 49.4 meter cubed. How about for the last part, part E? Well, you can use the same type of equation, but we're given the mass. Well, to convert back and forth, divide by the molar mass. And so when you do that with the mass of 29 kilograms, the volume for the last part E is 27.2 meters cubed. Amagat's model. Dalton's model gave us the partial pressure concept, very useful for ideal gas mixtures. It's used a whole lot more than Amagat's model, which gives us the concept of partial volumes, but you'll still see partial volumes discussed out there when you have ideal gas mixtures. So a mixture of several ideal gases, here just showing 1 and 2, so red component 1 and blue component 2. We'll have a total volume equal to the sum of the volumes of the constituents as if they were alone at the same temperature and pressure as the mixture. So this original total volume is the sum of a partial volume and a partial volume. If I have 2, then it's just 2 components. And this partial volume is for the same temperature and the same pressure. So what you're doing conceptually is partitioning off and saying all of this component is isolated to this volume, but it has the same net or total temperature and pressure. Go ahead and write down the equation for V. It's going to behave as an ideal gas. So it's going to be the total number of moles, R bar T divided by P. True? And in general, you could write down the equation for the volume of any species component V sub I is equal to the number of moles of I, R bar, that original temperature, and same pressure. So you take this equation, use it and divide both sides by V, and then you'll get, when you divide over here, it's N R bar T over P. So you're dividing like that, and R bars T over P go, and you're left with that this V sub I, the partial volume, divided by the total volume is equal to the mole fraction. And a lot of times you leave it like that. In some applications, they may tell you not the molar analysis, but the volumetric analysis of the gas. They'll say, oh, the gas is 30% CO2 and 70% nitrogen, but it's a volumetric analysis. What? I know how to handle mass analysis, and I know how to handle molar analysis, but they're using this term volumetric analysis. Well, guess what? The percent for the volumetric analysis is exactly the same as the percent for the molar analysis. See? Also, they'll use terms like gravimetric analysis. What? Weight? Remember what big M, when I learned it way back when, it was not the molar mass, it was the molecular weight. But then it was the ratio of the mass per amount. So where did weight come in there? Well, it's a carryover, and I think a lot of textbooks still use molecular weight, right? Well, if they say the gravimetric analysis showed that it was 30% carbon dioxide and 70% nitrogen, that's saying the mass fractions are 30% and 70. So remember those two things, okay? Volumetric analysis, molar analysis. For ideal gas mixtures, same thing. Gravimetric analysis and mass analysis, same thing. Nitrogen at a given temperature of 40 C and 150 kilopascal occupies a closed rigid container having a volume of 4 cubic meters. 6 kilograms of oxygen are added to the container, and the final mixture temperature is 60 degrees C. So think about it. You start here, and it's just nitrogen in this fixed rigid container, and you end and you have both nitrogen and oxygen in, and they tell you how much mass of the oxygen's in there, because they say I put in 6 kilograms, so the mass of the oxygen that they put in is 6 kilograms. The temperature one is 40 degrees C. It's 313 Kelvin. The pressure initially is 150 kilopascal when it's just nitrogen by itself. And the volume of the tank doesn't change. It's always just 4 cubic meters. And so the final temperature is 60 degrees C, 333. Let's take a look at what they ask us to solve for. Molar analysis of the final mixture. They want Y of O2 and Y of N2, the final mixture. Gravimetric analysis of the final mixture. Here's that gravimetric. It's a mass analysis. They want the mass fractions, right? So I'm just going to put the MF. MfO2 and MfN2. The apparent molar mass of the final mixture, cap M. The final mixture pressure, P2 in kilopascal. And the partial volume of N2 in the final mixture. I'm going to say V sub N2. It's as if you could push all the nitrogen to the top. What would this volume be? That's our partial volume concept, right? Get the number of moles of O2 that have been introduced. How would I do that? Is it the mass of the O2 that was introduced? Let me put a lowercase m. Divided by cap M of diatomic oxygen. Roughly, what's the molar mass of oxygen? 16 and 16, 32. 32 kilograms per kilomole. All right. How about this? Can I get the number of moles of the N2 that were originally in the tank? Ideal gas equation, right? So it'd be the pressure, the volume divided by R bar T. And so I get the number of moles of N2. Now that I have the number of moles of N2 and the number of moles of oxygen, can I add them up to get the total number of moles in the mixture? And then the mole fraction of the N2 is just the number of moles of N2 divided by cap N, and the mole fraction of oxygen, the number of moles of O2 divided by N. Part A is done. What about gravimetric analysis of the final mixture? Well, I will do the same thing. I need to get the total mass is the mass of the N2 plus the mass of the O2. One of these we know right away, the mass of the oxygen. It was 6 kilograms was introduced. How do I get the mass of the nitrogen? You calculated already the number of moles of the nitrogen. Multiply that by the molar mass of the nitrogen. Nitrogen roughly is N2 diatomic nitrogen. Molar mass 14 and 14, around 28. Once I have that, then the mass fraction of the nitrogen is the mass of the nitrogen divided by the total mass, and the mass fraction of the oxygen is the mass of the oxygen divided by the total mass. Done with part B? How about the apparent molar mass of the final mixture, cap M? How about I pause and walk around a little bit, see what you're at, where you're at. All right. So the molar mass, a lot of people, congratulations, it's the mass of the mixture divided by the total number of moles of the mixture. And then the final mixture pressure, how do you want to solve for P2? Use ideal gas equation. So maybe you know the total number of moles that are in the tank or container. R bar, the final temperature divided by the volume. I think each one of those we know, right? Or have calculated. And then what's the partial volume of the nitrogen in the final mixture? V2. How are you going to solve for V2? I'm going to pause and walk around and see what you get for V2. All right, to calculate the last part, right? The partial volume of the nitrogen, you can do it a couple ways. You can do the mole fraction of the nitrogen times the volume of the tank. Real straightforward. You could also do the ideal gas equation where you have to have the number of moles of nitrogen, calculated previously, times R bar T2, the final temperature, divided by P2, which you just calculated. But I think what you'll find is it'll unravel and go to the simple form right there. It's just mole fraction times the volume. Make sense? All right. Now we want to calculate the internal energy, the enthalpy, the entropy, and the specific heats for ideal gas mixtures. You can have the same molar approach or the same mass approach as what we did before. On a molar basis, does it make sense that if I wanted to calculate the internal energy, cap U, in units like kilojoules, for the total mixture, it's equal to the sum, the number of moles of each component times its specific internal energy on a molar basis, right? U bar for each component I. And on a mass basis, cap U is equal to the sum of Mi, the mass of each component in the mixture, times U sub I. Does that make sense? Would it also make sense that if I was able to calculate cap U, I could say, well, it's the product of the total mass of the mixture times, it's the product of the total number of moles of the mixture times U bar of the mixture. the specific internal energy on a molar basis for the mixture. So what we find is that U bar is equal to, divide over by N. What does the N sub I over N become? Yi, the mole fractions. It's the sum of Yi times U bar I. So the molar specific internal energy is the sum of the mole fractions times each component's molar internal energy. Likewise, you do the same thing here. This is the mass times U is equal to the sum of M sub I, U sub I, and then you get that the mixture internal energy is equal to the sum of the mass fractions times each component's internal energy. Can you believe that that would be the same for H? H bar, the same type of algorithm, is equal to the sum of Yi H bar I. And on a mass basis, the mixture enthalpy is equal to the sum of the mass fraction for each component times each component's enthalpy. How about entropy? Well, maybe it's the same type of approach. We have that the S bar is equal to the sum of Yi S bar I's, and S is equal to the sum of the mass fraction I's times S I's. Make sense? Last is specific heats. Well, what is the definition of C sub V? Is it the rate of change of U with respect to temperature holding volume constant? And this whole chapter was devoted to ideal gas mixtures. Well, if each component's an ideal gas, what does that partial derivative turn into? An ordinary derivative. So it's just du dt. Forget about holding V constant. That's just C sub V. So we come back to this equation, maybe right here, and we take the derivative with respect to temperature of that whole equation. Okay? So if you do that, what you find is you'll get the derivative of U bar with respect to temperature is equal to, take the derivative inside that summation, you'll get the sum of Yi derivative of U bar I with respect to temperature. Well, I have to scoot down a little bit, sorry. This is C sub V bar of the mixture. It's the specific heat constant volume of the mixture on a molar basis, is equal to the sum of the mole fractions times C sub V I bar. And if you do it on a mass basis, you get the same similar result. C sub V is equal to the sum of M sub Fi CVI. And if you do it for C sub P bar is equal to the sum of Yi C sub Pi bar. Or C sub P of the mixture is the sum of the mass fractions times C sub Pi. With that, I'm out of time. Thank you for your attention.